This is an example problem for our textbook, Engineering Fluid Mechanics. This problem involves the ideal gas law. Here is the problem statement. To interpret the problem, I sketch the tank, label the gas, its quantity. I decide to work in SI, so the pressure of 2 bars becomes 200 kPa, and the temperature of 70 Fahrenheit becomes 294 K. I list the problem goal. To reach the goal, I notice that the problem involves a number of moles and a gas, and this suggests the ideal gas law. I recall that the ideal gas law has 3 forms: the mass form, the density form, and the mole form. And since the problem involves moles, I'll want to use this. And what you want to notice in these equations is that these first two involve the specific gas constant, and this one involves the universal gas constant. In looking at this equation, it does not have my goal diameter, so I'm going to start with the volume of a sphere because that does include diameter. Problem goal appears here. And if I can now find an equation for volume, I can solve for the problem goal. Volume appears in the ideal gas law. The pressure was specified, the number of moles is known. That's the universal gas constant. Temperature is given. Thus I have 2 equations and 2 unknowns, diameter and volume. So my plan is to solve the ideal gas law for the volume and then go back to the sphere volume equation and solve for the diameter. Next, I wrote down the steps of my plan, step 1 and step 2. Then I executed my plan. The volume came out to be 0.112 cubic meters. The diameter of the tank was 1.96 feet. Use SI whenever you can. Saves time, eliminates mistakes. Remember, the ideal gas law has 3 forms: the density form, the mass form, and the mole form. Use whichever form is easiest on a given problem. And it's also useful to remember that the ideal gas law involves sometimes the universal gas constant, sometimes the specific gas constant. The universal gas constant here goes with the mole form, and the specific gas constant here goes with the mass form and the density form of the ideal gas law. Here's a way to validate this problem. At standard conditions, 1 mole of an ideal gas occupies a volume of exactly 224 liters. Therefore, 10 moles, which was in the case for this problem, should have a volume of 224 liters. And in our problem, the pressure wasn't 1 atmosphere, it was 2 atmospheres, so we would expect half of this, or 112 liters. And if you look at the calculated volume, you'll see that it came out very close to this number. This provides a way to check this problem. Thank you very much for listening to this. I really appreciate it.